Hey everybody, this is Miss Eisencraft with the last station, the significant test for mean station. Okay, so there was a simple random sample of 100 postal worker employees, and they were asking them how long they had worked for the Postal Service, and the average of their sample was 7 years, and their standard deviation was 2 years. So this is stats from their sample. So this is X bar. This is the average from their sample, and this is the standard deviation from their sample. Okay. Um, so they're testing it against this old information from 20 years ago that said the average length a postal worker has been working at the post office is 7.5 years. Well, this is different, but is it statistically significant? So it's less, but they're just asking, is it different? So there's the null. We're testing if it's different, has changed. Okay. The 20 years ago doesn't matter. Just all right, so if they ask for a p-value, we have to perform the test. I'm going to do it with my calculator versus by hand. So what I'm going to do is I'm going to go to stat, test. And since this is means, right, and we don't have the true standard deviation, the calculator is going to have to use this. It's going to be approximating. We have to use the t-distribution. So this is a t-test, number 2. And since we have stats, we don't have data. We don't have individual pieces of data. Like we don't have the 100 pieces of information. Like I worked here for 5 years. I've worked here for 8 years. We don't have that. We're entering in a list. We have the summary statistics. We highlight this. Then we go here where the nulls we're testing against the old average or what they're claiming the average is. Here's our sample average, our standard deviation, our sample size, and we're testing that it's just different. So let's go ahead and draw it. Not equal will always show up on 2 tails. And we're looking for the p-value. So typically when you're doing p-value by hand, you have to double it, but the calculator, because you hit not equals, it's doubling it for you. So the p-value, your t-value for your test statistic is negative 2.5 and positive 2.5. And that's a p-value of 0.014. Okay, so I guess what that's, if you would have done the individual stats, you would have gotten like 0.007 over here and 0.007 over here. But the calculator added those up for you because whenever you would have done that fraction of like x bar minus mu over, s of x over square root of n, you would have gotten negative 2.5. And then since it's different, you're looking on both sides, you would have doubled it. There's your p-value. Okay, so the fun part, where does that fall? Well, since this is in the thousands, it's kind of hard for me to read decimals when they're all in different place values. So this is not larger than this, no. Is it between this? Well, let's see, 0.100 and point. No, is this between 50 and 100? No, this is 14. 0.050 and 0.010, 10 and 50. Yeah, I had to write them out to the thousandths. This was messing with my brain. It's not below that. And yes, it can be determined. Okay. We used the p-value on a t-distribution. You can't do a p-value from a z-distribution since you don't know the standard deviation. All right, so now it's asking, do you have convincing evidence at this level, at the 0.05 level, that the average time a postal worker has worked from the Postal Service is different from 20 years ago? Yes. Okay, so yes. P equals 0.014, which is less than 0.05. Okay, so yes, you have sufficient. That was our level. Okay, how about, do you have convincing evidence at the 0.01 level? No. P equals 0.014, which is not less than. I think you can say is greater than. I think that's how they say in your book. We're going to go with this. Right? We need it to be under there to prove that, and it's not. Hope that helps. I'm so tired and I'm not talking clearly.